Welcome to the first lecture on electronic circuit design. In this lecture, we will study frequency response of amplifiers, and we will continue studying the frequency response for the next few lectures. Before this, in our last course, Electronic Devices and Circuits, EDC, we have studied, in addition to many other circuits, we have studied this voltage divider biased BJT amplifier, where this blue is the biasing circuit and this green is it contains the coupling capacitors C1 and C3, the bypass capacitor, the load resistor, and the AC input source to make it an AC amplifier. We have studied these kind of circuits in our last course, electronic devices and circuits. Right. In this course, we'll start studying frequency response of these amplifiers that we have been studying in our last course. Right. What does the frequency response means? It means that if we apply the input signal, of course, this input signal is sinusoidal signal, and it has some magnitude, a mean magnitude, and a frequency. What does the frequency mean? This is a signal or having certain frequency, but this signal has a frequency almost double than this signal, this upper signal. And of course, this signal has a lower frequency compared to both these signals. Right, so if we apply signals of varying frequency having the same magnitude, and we want to see what is the effect on amplification of the transistor-based amplifier circuits. Either they can be BJT-based amplifiers or they can be FET-based amplifiers. We'll study both. Right, so in order to start with, let's see what is the effect of coupling capacitors on low and high input, on signals with low and high frequency, This one is a low frequency, this one is a higher frequency. Right, so what is the effect of coupling capacitors? We know that these two capacitors, C1 and C3, they are coupling capacitors. They are there to stop this higher magnitude DC currents to flow through this small valued AC input source so that it can be saved from being destroyed. As well as on the output side, this C3 ensures that there is no DC available across RL and we get only AC there. Right, so this is the purpose of having these coupling capacitors C1 and C3. Let's see what happens to the AC voltage gain at lower frequency when we have these coupling capacitors placed in. Right, so C1 and C3 are coupling capacitors, and we know from elementary circuit analysis courses that Xc, the capacitive reactance of a capacitor, is 1 over 2 pi Fc, where F is the input frequency and C is the value of capacitance in microfarads or picofarad or nanofarad. Right, this means Xc is inversely proportional to frequency. So at lower frequency, of course, we'll have a higher Xc. At lower frequency, Xc is higher. This means at lower frequency, Xc1 and Xc3, they are both large. So what is the disadvantage of having larger Xc1? This having a larger impedance here and a larger impedance there. what can be the disadvantage? It's obvious. The disadvantage is that if we have a large impedance here, there will be a large voltage drop across this capacitor. This means we'll get a smaller voltage here to be amplified. And once it is amplified, a part of it, even in fact, a larger part of it will be dropped across this capacitor C3 and we'll get a smaller voltage across RL. So in short, the voltage gain from the input V in to the output voltage V across RL is reduced. So the disadvantage is that we have a smaller voltage gain if we have large capacitance, if a large impedance here and a large impedance here. Right, so this is a disadvantage of having C1 and C3 if we work at really small frequency values. But what happens at higher frequency? Oh, they are perfectly fine. Why? Because at higher frequency, if this F is very large, this means F is large, this means XC is small. If XC is small, this means they offer very small impedance in series with this source and in series with this RL, and that's fine. We'll have a fairly large voltage gain at the output. And another problem introduced by C1 and C3 is the phase lead issue. Why? Because these are capacitors, and if we see this capacitor comes in parallel with these two capacitors, the input R in, that is composed of R1 in parallel with R2. So it becomes a series RC, sorry, it becomes in series with this. So this becomes a series RC circuit, and we know that for a series RC circuit, the current is leading the applied voltage, and the voltage drop across the resistor is also leading the input voltage. So there will be some leading part. Similarly, this is also a series RC circuit. This is also a series RC circuit, and there will be a phase lead across the voltage that we get across, and there will be a phase lead in the voltage that we get across RL. So that is another issue in addition to a smaller voltage gain at lower frequencies. What happens to the bypass capacitor? This is the bypass capacitor C2. It is there. Why is it there? It is there to bypass this RE, and we assume that for AC, this C2 will be shorted, will act like a short circuit and offer a resistance approximately equal to 0 ohms. And then this 0 ohm comes in parallel with this RE. The parallel combination is also very close to 0, and we have the gain AV, that is minus RC over this small RE, the junction resistance, the maximum voltage gain. So it is there to increase voltage gain in short. In our last course, EDC, electronic device and circuits, we placed this C2 to have a larger voltage gain. But what happens at lower frequencies? If we work at lower frequency, it comes in parallel with RE. This means if it is at a lower frequency, and of course XC is inversely proportional to F, so at lower frequency, its magnitude, of course, XC, the magnitude of XC is larger. If it is large, a large value of XC comes in parallel with RE. RE is already large. So a large value in parallel with a large value, that is half of that. If they are equal, they are half that. But still, the value is large, and that comes in series with the small RE, the junction resistance, and we get a smaller voltage gain. So at lower frequency, C2 plays its role to reduce voltage gain. But at higher frequency, it is perfectly fine because at higher frequency, XC is small, and at very high frequency, it is almost equal to 0. That is RC AV is AV is then minus RC over RE, and that is what is desired. So it is perfectly fine at higher frequency, but at lower frequency, in short, at lower frequency, both the coupling capacitors C1 and C3 and the bypass capacitor C2, they work to reduce the overall voltage gain of this amplifier. What happens at higher frequency, at higher frequencies, and what is the role of having reduced voltage gain at higher frequencies? That is the role played by the internal transistor capacitances. For a BJT, we have these two capacitances that play their role. The input capacitance between base and emitter junction, the output capacitance between base and collector junction. Sometimes they are plotted with some dots. This means they are not externally connected, but they are there. They are internal junction capacitances. They are not connected from outside. In fact, they are some internal junction capacitances. CBE is base emitter capacitance. CBC is base collector capacitance. Sometimes it's called input capacitance. This is called output capacitance. But they are very small. They are there. They are there because of the fabrication of semiconductor. Of course, they are not externally connected. This you should keep in mind. They are never externally connected. They are there. They are internally connected. They are internally present due to the junctions, and they play their role. Let's see how. They are very small. Something that we must know about CBE and CBC is that they are actually very small. This means that what happens at lower frequencies. The small value, F is small, CPE is also small. So we have one small value multiplied by another small value. A small value multiplied by another small value gives us, of course, a small value. And that small value, once in the denominator, it's a very small value in denominator. So what we get as XBE, of course, a larger value. Of course, a larger value. So XBE is large at lower frequency. Oh, no issue. But at lower frequency, we have already studied that the externally connected capacitors C1, C2, and C3, they tend to reduce the gain of the amplifier. So at lower frequencies, these three externally connected capacitors, they reduce the gain. But at higher frequency, let's see which capacitances play their role to reduce the gain. That is these internal junction capacitances. For large value of F, this value is large, but CBE remains the same. It's a small value. So now we have a larger value multiplied by a smaller value. So the result is not that small as it was here. It's not that small. It's small, but it's not that small. So XBE would be smaller compared to the XBE that we had here. Right. So now we have a smaller XBE. Smaller XBE causes short circuiting or reduced impedances at junctions, which plays its role to drop the overall voltage gain. So in short, we have two types of capacitances in a transistor based amplifier. The externally connected capacitors, they play their role to reduce the overall voltage gain at lower frequencies, and these junction capacitances, they are built in, they are not externally connected, they are there, they are part of the transistor, and they play their role to reduce the overall voltage gain at higher frequencies. So both at low frequencies and at higher frequencies, these amplifiers, no matter if they are made of BJTs or FETs, their gains are small. But for middle values of frequencies, of course, the gain is larger compared to the gain that we get at lower frequencies and higher frequencies. In fact, they work in a band of frequencies like this. So for low frequencies, the voltage gain is smaller. If we plot voltage gain on y-axis and frequency on x-axis. So for smaller values of frequencies, the gain is small. For higher values of frequencies, the gain is again small. But for middle values of frequencies, the gain is large. So they work in a band. We'll explore this phenomena further in our upcoming lectures, but in the lecture to come, in the very next lecture, we will study Miller's theorem on the junction capacitances. That's all for this lecture. Thank you.